everyone, and thanks for coming today. My name is Asmaa Sharif. I am an assistant professor at University of Dammam, Saudi Arabia. This is my second year at MIT. Today's presentation will be on photoelectric hot electron generation, transfer, and injection for the metallic semiconductor photonic crystal coated with gold nanorods. My advisor is Professor Sang-Guk Kim from the Mechanical Engineering Department. Surprisingly, oil will not disappear, and we still have oil for more than 100 years. Renewable energy goal is not to replace the existing oil, but to minimize the emission of carbon dioxide. Since the Industrial Revolution, the amount of carbon dioxide increases from 280 to 407 parts per million in 2016. So there is an urgent need to minimize this emission, otherwise there will be a real disaster. So solar is good, but it is not true. It has intermittency. We get a lot of solar energy during the day, but we also need a lot during a night. And without making it storable like fuel, that does not help. By producing hydrogen from solar, storable energy can solve this problem, and that justifies our solar water splitting project. The concept of water splitting have been shown 30 years ago in Honda's paper, but the efficiency was very low, not more than 1 or 2%. So what are the issues? If we use silicon, silicon will start to corrode. So people have chosen titanium dioxide, which is stable in chemical reaction and electrolyte environment, which is low cost and easy to fabricate. But the problem with titanium dioxide, it has wide band gap, which means titanium dioxide will absorb only the UV light. So people started to add a second material interfaced with the semiconductor to collect sub-band gap photon. By having lower band gap material, lower energy photon can be absorbed and then generate electron-hole pairs, then inject them into the semiconductor to be collected. The most well-known material is the dye sensitized, and that's how the dyes work. The problem with this molecule, they have low efficiency, and they will degrade with the time. So people started to add a metal as a second material. The metal will absorb light and then generate so-called hot electrons, which are electrons not in thermal equilibrium with electron gas, and they usually have energy higher than the energy expected from the thermal distribution. Since metals such as noble metal are solid state and stable, this injection of hot electrons seems to be a promising method. But we all know that the bulk metal is pretty good reflector, so how can we make the metal a good absorber is a key point for hot electron application. Recent publication in our group demonstrate that two-dimension metallic dielectric photonic crystal can achieve a broadband absorption. And our idea was to collect sub-band gap photocurrent by absorbing more photons and then generating more hot electrons, then inject them into the semiconductor to be collected. This figure shows how our device works. The metal, which is in our case is the gold, will absorb light and then generate hot electrons via inter or intra-band transition. Then an effective way to collect these hot electrons to form Schottky junction with N-type semiconductor. What we achieved, first in the optical simulation using finite different time domain, we sweep various parameters to see the absorption behavior, and also we use different thicknesses for each layer to find the optimized thickness for each layer. Here is the simulated absorption spectrum, which shows pretty good absorption, around 70% up to 1.5 micron. And this result matches with the experimental result, especially below 1.5 micron. So this device, our device, absorb a lot of light due to enhancement in different modes supported by the cavity structure. The question was, could we collect hot electrons from this absorption? Then after that, we measured the photoresponse. There is a peak centered at 590 nanometer with a full width at half maximum at 235 nanometer. So there was improvement in the photoresponse factor of 4.5 compared with a flat chip. Also, measurements shows that the thin metal is the better for hot electron collection efficiency. For the mode analysis, also using finite different time domain, we used dipole source, which provide the system with electromagnetic field. Then the time monitor will record the electric field with the time. After we apply the Fourier transform, we will have this figure. Here is the result after we add all the time monitors using different thicknesses of gold. The first peak, which is the most dominant, refers to the waveguide mode at 500 nanometer. The second peak, which is at 600 nanometer, refers to the surface plasmon mode, propagating at the interface titanium dioxide and gold. The third peak, which is pretty small and not clear, refers to the cavity mode at 700 nanometer. By comparing this result with the result from our previous slide for the photoresponse, we can say that only surface plasmon mode will improve the hot electron generation. So we achieve broadband absorption due to enhancement in different modes supported by the cavity structure. Also, we achieve subband gap photoresponse at 590 nanometer due to surface plasmon mode, and we are still working to find why not the cavity mode? Why not the waveguide mode? The question was, could we collect hot electron generation and injection in the range from 700 to 900 nanometer? In order to have hot electron generation and injection at 700 nanometer, we coated our device with gold nanorods with an aspect ratio of 3. Here the dimensions are 15 and 45 nanometer. In order to find what is the optimum density, 4 different suspensions were prepared using different concentrations. We can see in this figure the absorption measurement for these different suspensions, and each plot refers to, there are 2 main peaks, refers to the transfer and longitudinal plasmon mode at 530 and 700 nanometer. Also, we can see that varying the concentration will alter the absorption behavior. Also, we don't want to use very high concentration because high concentration will start to block the cavity. The second figure shows the zeta potential, and we can see from this figure the higher acidity will give the higher zeta potential. In order to find what is the optimum density and in order to increase the absorption and the efficiency in our device, we need to control the density of gold nanorods. So high concentration will start to block the cavity by agglomeration. Low absorption will lead to low efficiency. So the sufficient coverage will make these gold nanorods well distributed, well uniform without blocking the cavity. And this is our goal. In order to find what is the optimum density, 4 gold slide coated with these different 4 suspensions using electrophoretic deposition. After applying electric field between these 2 electrodes, gold nanorods with a positive charge will move toward the cathode and deposit it on the top of the surface. The result, we can see the result in these SEM images. So from these SEM images, we can say that the optimum density in our case without blocking the surface can be either with an area density 38% or 17%. And the second figure shows the absorption after applying electrophoretic deposition and the maximum absorption at 700 nanometer with an area density of 38%. Then after we find what is the optimum density, we apply the same thing on the metallic semiconductor photonic crystal using the same setup. The result is gold nanorods well distributed, well uniform on the top of the device and also on the sidewall of the micro or nano cavity. Then after that, we measure the photoresponse on a flat device. The blue curve shows the photoresponse without nanorods. The red curve shows the photoresponse with nanorods with an area density of 38%. At 530 nanometer, there is improvement in the photoresponse. However, there is no improvement and there is no peak at 700 nanometer. Our hypothesis was because all gold nanorods are deposited horizontally on the top of the surface, that means only hot electron generated by the transfer plasmon mode will inject into the semiconductor. And it is clearly in gold nanorods there are two momentum directions. Also, it is clearly there is no injection at 700 nanometer if all gold nanorods are deposited horizontally. So in this case, what is the factor that affects the hot electron collection efficiency? Electron momentum needs to be considered. If we assume that generated hot electrons can have randomly directed momentum, then for a successful injection, we need both energy and right direction, which means that only hot electrons with large enough momentum component perpendicular to the interface can cross the barrier. And if we look at momentum space, it can be shown as an effective cone, which means that only hot electrons with momentum component lie in this cone can cross the barrier. From this hypothesis, we started to design our new model for vertical gold nanorods. Here is the core function used to calculate hot electron generation and injection for horizontal and vertical gold nanorods. N is the generation rate, which includes both electric field enhanced by the plasma resonance and electrons. R injection is the injection rate, and the reason we are considering the injection here because some of hot electrons will lose their energy through their journey to the interface. So the first figure shows distribution of hot electrons at momentum space. The second figure shows the distribution of hot electrons at two-dimensional plots. And the different colors shows distribution at different momentum, which means that in red region there is a lot of hot electrons, and only these hot electrons below the Schottky barrier will have enough energy to cross the barrier. This is the result from our calculation, which was interested result. And we can see there are two main peaks for generation and injection rate at 496 nanometer and 720 nanometer refers to the transfer and longitudinal plasma mode for horizontal and vertical gold nanorods. And this result matches with the internal quantum efficiency, especially at these two main peaks. After that, we did some simulation using finite different time domain for gold nanorods array with the dimensions of 15 and 45 nanometer. From this figure, we can see that at 500 nanometer at 0 degree, there is a peak, and this peak is decreasing with increasing the angle of polarization of light. On the other hand, at 700 nanometer, there is no peak, and this peak is increasing with increasing the angle of polarization of light. Also, there are some other peaks above 700 nanometer. For the device fabrication, it includes two main parts. The first part started with 6-inch silicon wafer, and on the top of the silicon, we deposited different layers using different fabrication techniques at MTL. So this cartoon shows our device. Here we have the silicon. On the top of the silicon, we have silicon dioxide, polysilicon, and around 75 nanometer titanium dioxide. And here we have thin gold layer, and on the side we have thick gold and thick titanium as electrodes for electrical measurement. The second part of the fabrication includes depositing vertical gold nanorods. In order to have high-resolution gold nanorods, we used the electron beam lithography technique to make holes on the top of the device. Here is the avionics we used to make these holes at building 24. And this figure shows how this technique works. So first, the E-beam will hit the first point and stop. Then it will hit the second point and stop. Then when the row ends, it will start the second row. So we need to address each point separately in a serial format, which is totally different from other techniques such as the stepper. The result is high-resolution holes with a diameter of 25 to 30 nanometer. And this SEM image was taken after we did it several times, and we found what is the optimum dose of electron beam in our case. The second part was to deposit or to evaporate around 75 nanometer gold inside these holes using electron beam evaporator. The result, high resolution gold nanorods with a diameter of 25 to 30 nanometer and length 75 nanometer, where the distance from center to center is 100 nanometer. After that, also, we deposited around 5 nanometer titanium below these rods as an adhesion layer. The result, then after that, we did some measurements such as IV curve. The blue curve shows the IV curve for a device without gold nanorods, and it shows good diode characteristic. The red curve with gold nanorods, and as we can see, it shows poor diode characteristic. Our hypothesis was because this poor diode characteristic comes from the titanium adhesion layer we deposited below the gold rods, and we are still working to find how can we improve our diode characteristic for the device. So being a chemist and coming from a chemistry background to a mechanical engineering department was a big challenge. Now, after I spent 2 years at MIT, I learned first optical simulation to simulate the organic or the metallic semiconductor photonic crystal and to show high absorption in solar spectrum region. And then I learned nanocavity fabrications at MTL, thanks to all MTL people for their help and support. After that, we measured the photoresponse. There was a peak centered at 590 nanometer with a full width at half maximum of 235 nanometer due to the surface plasma mode. In order to have hot electron generation and injection at 700 nanometer, we coated our device with gold nanorods with an aspect ratio of 3. Thanks to Professor Colin Bewey for his help and advice in this part. After that, we did some measurement, absorption measurement, then photoresponse measurement for a flat device without gold nanorods as shown in the blue peak, in the blue curve, and with nanorods as shown, horizontal nanorod as shown in the red curve. At 530 nanometer, there was improvement in the photoresponse. However, there was no peak at 700 nanometer. And as I mentioned, our hypothesis was because all gold nanorods were deposited horizontally, that means only hot electron generated from the transfer plasma mode will inject into the semiconductor. Then we started to think about depositing vertical gold nanorods. Then I learned how to use the E-beam evaporator, how to use the E-beam lithography, and I think this is a good opportunity to transfer all this knowledge back home at University of Dammam. In addition to the work I presented today, there is also a side work collaborating with Professor Vladimir working on organic solar cell. The key idea for the organic solar cell is that the organic layer cannot be thin. If it is thin, we'll have low absorption, and that will lead to low efficiency. So in order to increase the efficiency in these cells, we use the cavity structure with a goal in our mind to achieve more than 10% efficiency. Also, I'm helping my colleague, Professor Weilich from SUTD, to simulate the organic solar cell with a goal to achieve cavity mode resonance to enhance the absorption to thin polymer layer. In my next few months at MIT, I'll continue fabricating and measuring photoresponse for a flat device coated with vertical gold nanorods. Also to understand the energy and momentum distribution for hot electron generated by decay for surface plasma pollution. Also how to induce multi-surface plasma mode, especially in the range from 700 to 900 nanometer. The entire research is about the cavity structure. An open question is, can we apply this technique in other applications, or what other applications we can use this technique in? It can be solar cells, it can be sensors, it can be organic solar cell, and that might feed my future work back home at University of Dammam. Finally, this is list of people I'd like to thank. It's a long list from various labs. I'd like to give my special thanks to my advisor, Professor Sang-Guk Kim, for his help, advice, and support. Also, my special thanks go to Kate Anderson and Teresa Worth for always being there. Results from MIT, journal publication, and conference publications, and one pending patent. Thank you.
Other questions? Asmaa, excellent work, mashallah. How easy do you think this can be transferred to the University of Dammam? Especially equipment-wise, I know that knowledge can.
It's not easy. Yeah, it's a hard work. It takes hard work. And first of all, if there is a will, there is a way. So, and we started actually 2 months ago. The chemistry department in my university started to study the feasibility for elaborating a solar cell lab. And they started to also to bring some machines, important machines for this kind of lab, such as the simulator, such as the evaporator. And with my help and with my colleagues' help, and collaborating with big institutions such as MIT and KFUPM, we can achieve this goal.
Yeah, the comment is that we have excellent labs in chemistry department, materials and nano technology center. We have also physics, and you are welcome to use them, because we would like you to continue on this really very important subject, very important achievement.
Jumair Al-Ghamdi already has written a proposal with me on solar cells, and it has been approved by Dammam University. So we like to collaborate on dye-sensitized solar cell, which is a little bit you mentioned in the early stage of your talk. We are working already together on some joint projects on solar cells. Most of the equipment I think we have in KFUPM, except maybe this e-beam what you are talking. I'm not sure if they have. They like to buy it, but I don't know what they have done already or not. So it's a really good opportunity for you to join some collaborative work with KFUPM faculty as well, so you can utilize the facilities easily. These free electron, what you are talking in metals, basically, they are responsible for surface plasma resonance enhanced. But these free electrons, they have very random motion and they can move in any direction. So they have different kinds of momentum, what you are talking, right? So how you can control this by just these vertical rods that you are talking?
So,
because free electron, basically you are exciting in gold. Then you transfer the energy to TiO2, right? This is the main purpose, because TiO2 absorbs only at 380 nanometer. And you want to shift to visible region so that you can harvest the whole solar spectrum. So how you control these electrons, because these electrons are random motion, they have what they call, they have a drift speed. And they can drift, I mean, in any direction. So how by these rods, vertical rods, how you can control, I did not understand it.
By depositing the gold nanorods, we can inject more longitudinal surface plasma mode. The majority of the hot electrons will be from the longitudinal plasma mode. And from our calculation, we found that by depositing vertical gold nanorod, and I presented already, we have 2 peaks, especially the one at 700 nanometer. So the calculation told us there will be injection.
Thank you.
Thank you.
Thank you. Thank you. I think we need to move on. So.